Connecting lightning protection to the main service ground rod involves several considerations. The inspector's requirement stems from the National Electrical Code and industry best practices, emphasizing the equalization of ground potential for safe and efficient energy dissipation. While directing lightning away from the service is a valid concern, the primary goal is to provide a safe discharge path. Connecting the lightning protection system to the service ground rod offers several advantages. Firstly, lower ground resistance is achieved. The service ground rod typically has lower ground resistance compared to a dedicated lightning ground rod. This connection reduces overall ground impedance, enabling more effective dissipation of lightning energy. Secondly, an enhanced path is created. This path, defined and continuous, provides a clear, low-resistance route for lightning energy, minimizing side flashes and arcing risks. Thirdly, a single grounding point simplifies maintenance and testing. This ensures a consistent and reliable grounding system. A compromise solution involves installing a dedicated lightning ground rod, positioned safely away from the service, and connecting the lightning protection system to both this dedicated rod and the service ground rod. This approach provides a low-resistance path while minimizing the potential for lightning energy to reach the service. Additional considerations are important. The lightning protection system should adhere to the manufacturer's specifications and local codes. Use high-quality materials like copper or aluminum for bonding and grounding. Protect grounding connections from corrosion and inspect them regularly. If the inspector insists on connecting the lightning protection to the service ground rod, comply to maintain safety and compliance. The equalization of potential is a key safety measure. When lightning strikes, it introduces a massive amount of energy into the grounding system. If the lightning protection system is not properly bonded to the service ground, significant potential differences can arise between different parts of the electrical system and the surrounding earth. These potential differences can create dangerous side flashes, where the lightning current jumps from one grounded object to another, potentially causing damage or injury. By bonding the lightning protection system to the service ground, you ensure that all grounded objects in the vicinity are at approximately the same potential. This minimizes the risk of side flashes and provides a safer environment. The NEC provides specific guidelines for grounding and bonding lightning protection systems. Section 250.106 covers lightning protection system grounding and bonding. It requires that the lightning protection system be bonded to the building or structure grounding system with conductors sized according to Table 250.102. These conductors must be installed in a manner that minimizes the impedance of the grounding path. The NEC also requires that the lightning protection system be bonded to any metal objects that are likely to become energized during a lightning strike, such as metal siding, gutters, and downspouts. This bonding helps to equalize the potential of these objects and reduce the risk of side flashes. In addition to the NEC requirements, there are other industry standards and best practices that should be followed when installing lightning protection systems. For example, the Lightning Protection Institute LPI provides detailed guidelines for the design and installation of lightning protection systems. These guidelines cover everything from the placement of air terminals to the selection of grounding conductors. It's important to consult with a qualified lightning protection contractor to ensure that your system is installed correctly and meets all applicable codes and standards. A qualified contractor will have the experience and knowledge to assess your specific needs and design a system that provides adequate protection for your home or business. When selecting a lightning protection contractor, be sure to check their credentials and experience. Look for contractors who are certified by the LPI or other recognized organizations. Ask for references and check their work history to ensure that they have a good reputation. Remember that lightning protection is a complex and specialized field. It's not something that you should attempt to do yourself unless you have the necessary training and experience. Hiring a qualified contractor is the best way to ensure that your system is installed correctly and provides effective protection against lightning strikes. Regular inspections and maintenance are also essential for ensuring the long-term effectiveness of your lightning protection system. The system should be inspected at least once a year by a qualified contractor. The inspection should include a visual examination of all components, including the air terminals, conductors, and grounding connections. Any damaged or corroded component should be replaced immediately. The grounding connection should also be tested to ensure that they are providing adequate grounding. If the ground resistance is too high, the grounding system may need to be improved. In addition to regular inspections, it's also important to perform maintenance on the system as needed. This may include cleaning the air terminals to remove dirt and debris, tightening loose connections, and repairing any damage caused by weather or other factors. By following these guidelines, you can help to ensure that your lightning protection system is providing effective protection against lightning strikes and keeping your home or business safe. In the context of electrical engineering, ground resistance, also known as earth resistance, is a critical parameter that affects the performance of grounding systems. It represents the opposition that the earth offers to the flow of electric current. A lower ground resistance allows for a more effective dissipation of fault currents, thereby ensuring the safety of personnel and equipment. Ground resistance is influenced by several factors, including soil composition, moisture content, temperature, and the type of grounding electrode used. Different types of soil have varying resistivities. For example, clay soils generally have lower resistivities compared to sandy soils. Moisture content plays a significant role, as water increases the conductivity of the soil. However, excessively high moisture levels can lead to corrosion of grounding electrodes. Temperature also affects soil resistivity, with low temperatures generally increasing resistivity. The type of grounding electrode, such as rods, plates, or grids, impacts the overall ground resistance. Ground rods are commonly used and are driven into the earth to establish a connection. The depth and number of ground rods can be adjusted to achieve the desired ground resistance. Ground plates provide a larger surface area for contact with the soil and are often used in areas with limited space. Ground grids consist of interconnected conductors buried in the earth, providing a low resistance path for fault currents. Measuring ground resistance is essential for verifying the effectiveness of a grounding system. Several methods are used for this purpose, including the fall of potential method, the slope method, and the stakeless method. The fall of potential method is the most commonly used technique and involves injecting a test current into the earth through a test electrode and measuring the voltage drop between the test electrode and a reference electrode. The ground resistance is then calculated using Ohm's law. The slope method is a variation of the fall of potential method and is used in situations where it is difficult to place the test electrode far enough away from the grounding electrode. The stakeless method, also known as the clamp-on method, uses a specialized clamp meter to measure the ground resistance without disconnecting the grounding electrode. This method is particularly useful for testing grounding systems in sensitive equipment or in areas where it is not possible to drive test electrodes into the ground. The NEC provides guidelines for ground resistance requirement. Section 250.56 specifies that the ground resistance shall not exceed 25 ohms for a single grounding electrode. If the ground resistance exceeds 25 ohms, an additional grounding electrode is required. The NEC also provides guidelines for the size and type of grounding conductors and electrodes. In addition to the NEC requirements, other industry standards and best practices should be followed. For example, the IEEE Standard 142, also known as the Green Book, provides detailed recommendations for grounding and bonding of electrical systems. Proper grounding is crucial for the safe and reliable operation of electrical systems. It helps to protect personnel from electric shock, prevent equipment damage, and reduce the risk of fire. Regular inspections and maintenance of grounding systems are essential for ensuring their effectiveness. This includes visually inspecting grounding electrodes and conductors for corrosion or damage, testing ground resistance, and repairing or replacing any defective components. Proper grounding techniques are also essential for electronic equipment. Sensitive electronic equipment is susceptible to damage from voltage surges and electrical noise. Proper grounding can help to protect this equipment from these disturbances. Shielded cables and surge suppressors are also commonly used to protect electronic equipment. In summary, ground resistance is a critical parameter that affects the performance of grounding systems. It is influenced by several factors, including soil composition, moisture content, temperature, and the type of grounding electrode used. Measuring ground resistance is essential for verifying the effectiveness of a grounding system. The NEC and other industry standards provide guidelines for ground resistance requirements and grounding practices. Proper grounding is crucial for the safe and reliable operation of electrical systems and for protecting personnel and equipment from electrical hazards. Bonding is a crucial aspect of electrical safety, aiming to equalize electrical potential between conductive parts of a system. This prevents dangerous voltage differences that could lead to electric shock or equipment damage. Bonding ensures a low impedance path for fault currents, facilitating the operation of overcurrent protective devices like circuit breakers and fuses. The NEC provides detailed requirements for bonding in Article 250. Specifically, Section 250.92 covers bonding of services, outlining how to connect various metallic components to ensure electrical continuity. Section 250.96 addresses bonding of other enclosures, emphasizing the need to bond metallic enclosures containing electrical conductors to ensure a safe path for fault current. Effective bonding involves connecting all non-current carrying metal parts of an electrical system to the grounding electrode conductor or to a common bonding point. This includes metal conduits, enclosures, equipment frames, and other conductive components. The bonding connections must be mechanically secure and provide a low impedance path for fault currents. Several methods are used for bonding, including bonding jumpers, bonding bushings, and grounding straps. Bonding jumpers are conductors used to connect two or more metal parts together. Bonding bushings are used to provide a bonding connection between a metal conduit and a metal enclosure. Grounding straps are flexible conductors used to bond equipment to a grounding electrode. Proper bonding techniques are essential for ensuring the safety of electrical systems. Improper bonding can create hazardous conditions, such as voltage differences between metal parts, which can lead to electric shock. It can also prevent overcurrent protective devices from operating correctly, increasing the risk of equipment damage or fire. Regular inspections and maintenance of bonding connections are essential for ensuring their effectiveness. This includes visually inspecting bonding conductors and connections for corrosion or damage, tightening loose connections, and repairing or replacing any defective components. The NEC requires that bonding connections be made in a manner that minimizes the impedance of the bonding path. This means that the bonding conductors must be sized appropriately and installed in a way that avoids sharp bends or long runs. The bonding connections must also be protected from corrosion. In addition to the NEC requirements, other industry standards and best practices should be followed. For example, the IEE Standard 142, also known as the Green Book, provides detailed recommendations for grounding and bonding of electrical systems. Proper bonding is crucial for the safe and reliable operation of electrical systems. It helps to protect personnel from electric shock, prevent equipment damage, and reduce the risk of fire. Regular inspections and maintenance of bonding connections are essential for ensuring their effectiveness. The location of the grounding electrode is another important consideration. The grounding electrode should be located as close as possible to the service entrance. This minimizes the length of the grounding electrode conductor and reduces the impedance of the grounding path. The grounding electrode should also be located in an area where the soil is moist and has a low resistivity. This helps to ensure that the grounding electrode is effective in dissipating fault currents. If the grounding electrode is located in an area where the soil is dry or has a high resistivity, it may be necessary to install additional grounding electrodes or to improve the soil conductivity by adding soil amendments. In addition to the grounding electrode, the grounding electrode conductor is also an important part of the grounding system. The grounding electrode conductor connects the grounding electrode to the service equipment. The grounding electrode conductor must be sized appropriately for the size of the service. The NEC provides guidelines for the size of the grounding electrode conductor in Table 250.66. The grounding electrode conductor must also be installed in a way that protects it from damage. The grounding electrode conductor should be run in conduit or otherwise protected from physical damage. The grounding electrode conductor should also be protected from corrosion. The grounding electrode conductor should be made of copper or other corrosion-resistant material. The NEC also requires that the grounding electrode conductor be continuous and without splices or joints. This helps to ensure that the grounding electrode conductor provides a low impedance path for fault currents. In summary, proper grounding and bonding are essential for the safe and reliable operation of electrical systems. Grounding provides a path for fault currents to return to the source, while bonding equalizes the potential of all non-current carrying metal parts of the system. The NEC provides detailed requirements for grounding and bonding, and it is important to follow these requirements to ensure the safety of electrical systems. Regular inspections and maintenance of grounding and bonding connections are also essential for ensuring their effectiveness. Proper surge protection also helps an electrical system. Surge protection devices, SPDs, are designed to protect electrical and electronic equipment from transient voltage surges. These surges can be caused by lightning strikes, utility switching, or internal equipment malfunctions. SPD work by diverting excess voltage away from sensitive equipment, preventing damage or failure. There are different types of SPD classified by their location in the electrical system and their surge handling capacity. Type 1 SPD are installed at the service entrance, providing protection for the entire facility. Type 2 SPD are installed at branch panels or sub-panels, protecting downstream circuits. Type 3 SPD are installed at the point of use, protecting individual equipment or appliances. The selection of an SPD depends on several factors, including the voltage and current rating of the electrical system, the expected surge levels, and the sensitivity of the equipment being protected. SPD are rated by their surge current capacity, measured in kiloamps. A higher surge current capacity indicates that the SPD can handle larger surges without failing. SPD are also rated by their voltage protection level, which is the maximum voltage that the SPD will allow to pass through to the protected equipment. A lower voltage protection level indicates that the SPD provides better protection. Proper installation of SPD is essential for their effectiveness. SPD should be installed by a qualified electrician in accordance with the manufacturer's instructions and the NEC. The SPD should be connected to a dedicated circuit breaker and should be properly grounded. Regular inspections and testing of SPD are also important for ensuring their effectiveness. SPD can degrade over time due to repeated surges. Regular testing can identify SPD that need to be replaced. In addition to SPD, other surge protection measures can be taken to protect electrical and electronic equipment. These measures include using shielded cables, isolating sensitive equipment from noisy circuits, and installing surge suppressors on individual appliances. Power conditioning equipment can also be used to protect sensitive equipment from voltage fluctuations and other power quality problems. Proper surge protection is essential for protecting electrical and electronic equipment from damage or failure. SPD are an important part of a comprehensive surge protection strategy. Regular inspections and testing of SPD are essential for ensuring their effectiveness. A lightning protection system installation is also important to adhere to. A lightning protection system is designed to protect a structure from damage caused by lightning strikes. The system consists of air terminals, conductors, and grounding electrodes. The air terminals are installed on the roof of the structure and are designed to intercept lightning strikes. The conductors are used to carry the lightning current from the air terminals to the grounding electrodes. The grounding electrodes are used to dissipate the lightning current into the earth. The design and installation of a lightning protection system should be performed by a qualified lightning protection contractor. The contractor will assess the specific needs of the structure and design a system that provides adequate protection. The installation should be performed in accordance with the manufacturer's instructions and the applicable codes and standards. Regular inspections and maintenance of a lightning protection system are essential for ensuring its effectiveness. The system should be inspected at least once a year by a qualified lightning protection contractor. The inspection should include a visual examination of all components, including the air terminals, conductors, and grounding electrodes. Any damaged or corroded component should be replaced immediately. The grounding connection should also be tested to ensure that they are providing adequate grounding. In addition to regular inspections, it's also important to perform maintenance on the system as needed. This may include cleaning the air terminals to remove dirt and debris, tightening loose connections, and repairing any damage caused by weather or other factors. Proper coordination with other trades is also important during the design and installation of a lightning protection system. The lightning protection contractor should work closely with the electrical contractor, the roofing contractor, and other trades to ensure that the system is properly integrated with the other building systems. The lightning protection system should be installed in a way that does not interfere with the operation of other building systems. The lightning protection contractor should also provide documentation to the building owner, including a description of the system, the installation procedures, and the maintenance requirements. In summary, a lightning protection system is designed to protect a structure from damage caused by lightning strikes. The system consists of air terminals, conductors, and grounding electrodes. The design and installation of a lightning protection system should be performed by a qualified lightning protection contractor. Regular inspections and maintenance of a lightning protection system are essential for ensuring its effectiveness.